Hello and welcome back to our machine design series. Today we are discussing viscosity. This is intended to be a review of this material for those of you who have taken a fluid dynamics course already. If you haven't taken a fluid dynamics course yet, hopefully this video will help get you up to speed enough that you can follow along for the rest of this section when we're talking about journal bearings, because viscosity plays an important role in the behavior of a journal bearing. And of course, I'm talking about the viscosity of the lubricant inside that journal bearing. So let's first consider the classical model of a Newtonian fluid. We're going to consider a flat plate with a Newtonian fluid sitting between that flat plate and the ground. And by the way, a Newtonian fluid means that it behaves as a normal type of fluid. When we think about fluids like air and water, those are Newtonian. If you, in contrast, think about something like quicksand, where the resistance of the fluid depends on the amount of shear stress that's actually applied to the fluid. So the more you struggle to get out of quicksand, right, the harder it is. That is typical behavior for a non-Newtonian fluid. But for most lubricants, it is a good assumption to say that they behave as a normal Newtonian fluid. All right, so here's our plate with a Newtonian fluid in this region between our plate and the ground. And I want you to think about this fluid as a bunch of different smaller slices stacked on top of one another. And when you visualize it that way, then when we think about what happens as this plate starts moving with a velocity u caused by the applied load F, these plates are going to start moving as well, sort of like this, right? The plate that is in contact with the slice of fluid that is in contact with this plate on the top, it's going to move with the plate. The plate or slice that is in contact with the ground down here is not going to move. It's going to stay in contact with the ground there. And then we're going to get this gradient of the slices in between. So these, you can think of this as like a deck of cards, the sliding with respect to one another. And we can model the shear stress in the fluid for a Newtonian fluid that is undergoing this type of scenario. The shear stress in the fluid that will develop is the applied load over the surface area, which is also equal to mu times the rate of change of velocity, where y is some distance from the ground to a particular location where we take the velocity. And remember, the velocity of the fluid is going to change depending on if you are at the top surface with the plate or on the bottom surface at the ground. When we're at the top with the plate, our velocity is equal to capital U. On the bottom, in contact with the ground, velocity is equal to 0, and we have this gradient in between. Let's label a couple other things. This total height here, we're going to call h. I guess that's it. All right, and then mu, this is the dynamic viscosity of the fluid. So when the viscosity is higher, the shear stress that develops in the fluid is going to also be higher. And this term is our rate of change of velocity. Now, for most lubricants, we're going to get the gradient that we have shown here, a linear velocity gradient. So that means that this rate of change of velocity is going to be constant, and it's just equal to u divided by h. So the velocity of the plate on top divided by the total height. We can plug this in to our equation for shear stress that we wrote above to get that the shear stress is equal to mu times u over h. Also note for viscosity that we have some new units to deal with. In the US customary system, these units are the pound second per inch squared. This is also a PSI second, which has another name, the reign. And this is named after Sir Osborne Reynolds, the same guy who came up with the Reynolds number. A reign. In SI units, this will just be a Pascal second. And you will probably see prefixes in front of each of these. Often we will see a micro reign or a micro PSI second, and for Pascal seconds, we will see milli Pascal seconds. So don't forget your prefixes. Mu is micro, and that's 10 to the negative 6. M stands for milli, and that's 10 to the negative 3. So, speaking of dynamic viscosities, let's take a look at some common dynamic viscosities of lubricants. First, I like to look at this chart on the right here and ask if anybody knows what the meaning of this W is in 20W50. Or for my car, my Subaru Forester, it takes 5W30. So if I usually get answers about the weight or the viscosity, but really this W, it actually stands for winter. So when we are in winter conditions, we want the oil to behave with less viscous behavior. So, let's think about this. So when it's cold outside, the oil in your engine is going to become more viscous, right? As temperature goes down, viscosity of fluids goes up. If we can come up with a chemical synthetic combination of lubricants that allows to sort of flatline that gradient so that when the temperature is colder, you still get a similar viscosity of the oil as when it's hot outside, then that would be advantageous to the performance of the engine. And so that is what this W means in 5W30. When we're in colder conditions, it behaves more like a grade 5 oil, and when we're in warmer conditions, it behaves like a grade 30. And then we have this other chart over here. These are the standard grades. They range from 10 to 70. The grades are given by SAE, so that SAE doesn't stand for anything else. It's just the Society of Automotive Engineers that come up with this grading system or standardize it. And so when we're solving problems to do with journal bearings, these charts will be incredibly useful if I need to specify a particular type of lubricant for an engine. I know that I want my viscosity to be, say, around 10 microrane, and I have a temperature of, let's say, 150 degrees Fahrenheit, then I can use this chart to determine, let's see, that's maybe a grade 60 lubricant that would be optimal for that application. We can also do it in the opposite direction. If we're given a certain grade of lubricant and a temperature, we can work out what the dynamic viscosity of that lubricant is to solve any problem that you might be given. So that's all I wanted to cover in this video. In the next one, we will talk about Petrov's journal bearings. So we'll start putting some of this discussion of viscosity and lubricants into practice through analyzing the friction and stresses that develop in a journal bearing. So stay tuned for that, and I hope you enjoyed this video. Thanks for watching.